Let's talk about the original design for this charging system, how it was supposed to function when the car was new. It's an ammeter based charging system. As in the introduction to the fixture, I've got 3 different ammeters set up here, but for this demonstration we're just going to use the middle one. It's the only one wired at this point in time. We're going to put some current through this system and take some measurements and see exactly where the current is flowing, just to kind of back up some of the other discussions we've had with diagrams. As I mentioned earlier, this power supply to the right is going to act as a stand-in for the alternator. At this point in time it's shut off, so the engine is not running. Battery's connected, key off, nothing going on. I'm going to turn on some headlights here. Headlights are powered from splice 1. Splice 1 is on the alternator side of the ammeter, black wire. We have an ammeter showing a discharge. This ammeter is registering 12.9 amps at this moment, discharging the battery. This current is flowing in through bulkhead connectors to the red lead on the red side of the ammeter, through the ammeter to the black wire back out to the charge wire. But in this case, our headlight's pulling its currents off of this splice right here. Can you see that splice? Let's turn the headlights off and start the car up. And that involves powering up this power supply. You will notice there's an ammeter on the power supply that tells us what the ammeter is doing. It's registering roughly 6 amps on that ammeter, and I'm confirming that with the digital one here. It says 6 amps, a little over 6 amps. What's going on here is there is no loads running. It's charging the battery because we sat there and pulled that current out of the battery a minute ago. 5 amps, it's going to, as soon as the battery reaches a full state of charge, this should be very little. You can see a charge indication on the ammeter. While it's charging, let's put that load back on it. About 13 amps that we measured a minute ago for all these headlights going. You'll notice it's not coming from the battery, it's coming from the alternator. And you'll also notice that the ammeter is centered, or pretty much centered. I see a little angle to the chart side, but that would be 3 amps of charging current. Let's turn off this load now and keep an eye on what the alternator's up to. By the way, if the engine's running, there will be other loads going on here besides just lights. Ignition system is going to consume some power. If there are other accessories turned on, windshield wipers, heater fans, all being fed from splice 1, some of that stuff goes through the ignition switch and puts a stress, roll this forward again, puts a stress on this Molex connector. A couple of terminals in here carry quite a bit of current. That's for a different video. Okay, so we demonstrated that this power is coming from the alternator. You can actually see it at the power supply there. We're going to turn this off. Nothing's really changing with charging. It's still charging the battery at about 3 amps, a little over 3 amps over there, a little bit of a charge indication. It'll continue that way until the battery's fully charged. Weak spots in this charging system. By far, the number 1 weak spot in this charging system is the Packard terminals at the bulkhead connector used in the charge circuit. This black wire from the alternator feed and this return battery passing through the bulkhead connector here. There really isn't an electrical need for a disconnect there, but that allows the car to be assembled quicker. Early car technology, electrical technology, did not involve any kind of waterproofing of these things. That was not sealed initially. There were some later attempts to try to put seals around some of that stuff, but it never really kept these dry in moist environments. They would corrode. Corrosion contributes to resistance. Resistance and current give you heat. And things, you get enough resistance and enough current, things are going to melt here. And it's going to snowball. The hotter it gets, the more resistance it builds. And you will get charging system issues, power supply issues. Splice 1 depends on getting power from one of these two, depending on if the engine's running. And if there's a problem here, you're going to have a problem in the rest of the electrical system. Troubleshooting resistance problems in this system. Voltage drop. Taking voltage drop measurements at various points throughout this while current is flowing can help you determine where exactly you're having issues. If it's not obvious with heat damage at the two charge path connections here, you're not sure exactly where you're having an issue, but you know you got an issue going on, you can take voltage drop measurements. Pretty simple, really, with some current flowing. Again, we have the power supply powered up over here. I see a total of about 25 amps. Check that. About 15 amps of combination of charging current and headlights, high beam headlights. But by the way, these headlights are not stock, bone stock. These are sealed beam halogens. They will pull a little more current than the original sealed beam headlights, but we're using them for this demonstration to get some current going. With current flowing, we can take some voltage measurements at various points in this circuit to determine, since the power is coming from, with current flowing, in this case most of it's coming from the alternator side, we can actually take some measurements between the power source and the load. In this case, I'm going to grab that high beam one right there. Now we're losing 1.86 volts between the headlight socket and the source of the power. Under these conditions, that's the alternator. We're losing that voltage through all these connections. Alternator feed on each side. It could be the male one, it could be the female one. We're probably losing a little bit through the splice. We may be losing some through the power feed to the headlight switch. The ammeter's not involved here. Could be these terminals here, here. Actually, if I move it around, you can see the voltage is moving around a little bit. That kind of tells me I got an issue with this wire connector at this switch. I mean, this is an old switch. It could be something internal to the switch. By the way, I can feel warmth on this wire from the 14th amps of current the lights are pulling. On the light circuit, by the way, this also includes the wiring out to the headlights. Actually, this wiring is in your dash harness running down to your dimmer switch. And also, by the way, I'm feeling warmth there. Could be these terminals here. You can jiggle things around and see that move a little bit. Could be the switch. Oh, look at that. I can get it past 2. Could be any number of things between the power source and the load. That, for the headlights, that would kind of bring this conversation towards headlight relays. And I do intend to make a make a video on headlight relays. And how to do that, and the advantages of it, and taking current stress off the factory small gauge wires. These are at best 16 gauge stock wiring for the headlights on most of these cars, and they worked fine for the old tungsten base sealed beams where they were pulling a few amps. It doesn't like this 13, 14. They're warm. We can also use a voltmeter to measure voltage drops on other circuits. Let's get back to the charge circuit for just a second. Let's get a load through that ammeter and see how much voltage we might be losing through the charge circuit. For that, I'm going to turn off the alternator. I'm going to turn the alternator off, effectively shutting off the engine basically. Now I've got current flowing through the ammeter. This light load is being routed through the ammeter through the same path here, headlight wiring, but now through splice 1 we're getting our power from the battery. So now we've got a path, we have a complete path through here from the battery to get to this load. Let's just see what's up overall with that load. Back on the high beams, I'm going to go here. Ooh, see, we're losing 2 volts through the factory wiring to get to those lights. Again, wire size, still got warm wires, actually warmer than I'm comfortable with. Again, that's if you just yank out your stock original lights and stick in sealed beam halogens. You're putting a lot of stress on wires not designed for that. Wires and connections. We're losing 2 volts through this wiring and the connections. Not good. Okay. I wanted to take some more precise measurements at various points and see where I might be losing the most voltage. I'm losing 0.08 just through that fuse of that current flowing. On the other side of the bulkhead connector, if I can get in there, we're losing 0.12 volts just through that connector, that bulkhead connector right there. Over at the ammeter, 0.31. So that's on the stud actually. Let me get on the wire. It's still 0.3. We're losing 0.3 of a volt. That tells me we're losing some voltage through splice 1. With this reading, so if I leave this here, come over here and grab this, I can isolate splice 1. Yeah, I'm losing 0.2 volts through that splice between that connector there and that connector there. Or the wire. Wire's included too. It could be losing some voltage through there. Let go. Let's see what we're losing through the ammeter. There's usually some voltage drop in the ammeter itself. Again, you got to have some current flowing to take these measurements. We're still at 12.5 amps. Stud to stud on this stock ammeter. 0.08. And ammeter wants to shut off. Did that lock in device? I can hit it again. There it goes. And you can use this method to go around and check voltage drop at various points to locate the biggest problem. Ideally, you want to go through and fix most of this, fix this connection or bypass it. Usually we're going to talk about a bypass too, something called a fleet bypass. The factory figured out some of this stuff pretty early on their fleet production, taxi cabs and police cars. They typically had a lot of extra stuff added to them, radios, lights, and such, and caused these issues to happen very quickly. Terminals burning up, wire sizing inadequate. I'm going to turn these headlights off here and cool these wires down. That's spooky. One of the reasons I do relays on everything, no matter what light it is. One of the things that we're going to do, I'll show you here real quick. The fleet bypass, essentially bulkhead disconnect bypasses. I'll show you what it looks like, and then I'll hook it up and we'll take some more take some more measurements. Bulkhead connector bypass for the charging circuit. Simple. It's the exact same thing they did on the fleet production. They don't run through the bulkhead connector on that charge path. Stand by. Okay, the fleet bypass or a bulkhead connector bypass. As mentioned, on fleet production, it was recognized that their charging system was not up to snuff on some high load applications. This is their first approach to that. It's a complete bypass of the charge circuits around the bulkhead connector. Although they weren't going to rework the entire dash harness, they routed extra wires through a grommet in the firewall from the battery to the alternator output using larger wires the factory would use. It's a 6 gauge. This is 8 gauge, and we have it connected to the fusible link. We'll talk more about fusible links in a bit. Straight to the ammeter. Is the ammeter showing up? Straight to the ammeter. Alternator feed also straight out through a grommet to the alternator. No disconnects at all at any of these two wires. Some applications, they put disconnects out on the engine harness side for other reasons, but they also failed and had issues. The best way to do this is no disconnects whatsoever. There's no need for any of that. You do need to leave the original 12 gauge ammeter lead onto the ammeter. This is powering splice 1 now. The other end of that splice that runs out to the bulkhead is not needed. You can leave it in there if you want. I've also, on some applications where I've got the harness completely unwrapped, I will take that out and run that back over to here as well to get a parallel run to splice 1, just to be sure splice 1 is getting what it needs. But you can leave it here. For stock loads in the dash harness, this is more than adequate. Well, let me rephrase that. This is adequate. On the engine harness side, I'll pull this out. I'll remove the original 12 gauge alternator feed unwrap the harness, take it out of the harness, and wrap this wire back up along with it. Let's take some measurements on this and see what kind of voltage drop numbers we have. So we're going to power things back up. I don't need to take any measurements here anymore. Let's get our load flowing. It's our 13 amps of current currently coming from the alternator. So the simulated alternator is in operation over there. You'll notice the ammeter is pretty much centered. Scoot that over just a little bit so you can see it a little better. Let's do some voltage drop tests here, see what we got going on. Again, since our voltage is coming from this side, we'll start with this. How much voltage are we losing to that charging system now? 0.06. Pretty sure we were losing about 2 volts there through the stock stuff. That's almost nothing. Actually, that looks like the ammeter reading. That would tell me that we're not losing anything through this wiring. Actually, one more measurement. Let's go from there to the lights themselves and see, because we still got the stock headlight wiring in place. We still got 1.7 volts from splice 1 through the light circuit, through the switch, through the dimmer switch, through the stock wires, out to the lights. That's a different subject. Headlight relays. Headlight relays. Let's see. Let's get some current through the ammeter. We turn the motor off basically, or stop the alternator output. Now we have a discharge at 14 amps is flowing through this ammeter. Let's see what kind of voltage drop numbers we have now. I would expect them to be roughly the same as what we saw before. And it is 0.07. So there's a little bit of loss through that ammeter, that particular, since we're speaking about that ammeter. It's stock, it's all stock. The terminations are stock the same way that they did it for the factory. Same nuts, the same insulator. Not even sure you're seeing that, you're not even seeing that. The ammeter we're running is all stock, but with good, tight connections. There's been no modifications to the ammeter whatsoever on that particular one. We'll be doing another more in-depth video on ammeters, comparing different ways we can terminate it here to make them have much less voltage drop. That pretty much covers how the system is supposed to work. One way to approach bypassing the real trouble with the system, the bulkhead connector.